Hello Sumit and hello Arun. We'll get started. So, I think I had introduced myself in the last session. I am a PhD scholar from Electrical Engineering Department of IIT Madras. We'll be taking a session that is a problem solving session every week, Friday from 6 p.m. to 8 p.m. We'll be covering some sample numericals from the content of this course Microwave Engineering, and we'll be dealing with every week the particular content of that particular week and some sample problem solving. We'll try to brief out what was covered in the previous week as a brief, and then we'll move on to discussions on some of the questions. So as I told in the last week, the course Microwave Engineering, the prerequisite is electromagnetic field theory. So you should have some knowledge and basics of electromagnetic field theory. And this course will definitely give you a foundations, basic principles of microwave, and also some applications in communication and other areas. And we'll be covering some microwave circuits and subsystems as well. So as this course is I have a question to you all. I would like you to introduce yourself so that we'll know each other. What is your requirement? And I request you to introduce, please, so that we'll get to know each other and make it more effective. Our course will interaction makes more effective. Please unmute yourself and kindly introduce.
Hello, ma'am. Very good evening.
Yeah.
This is Sumit Kumar from this
Yes.
side.
Yeah. Yeah.
And, ma'am, presently I am working in the research field, which
Okay.
is related with microwave engineering.
Okay.
So, I want to update some theoretical portion of microwave engineering.
Okay.
So, that's
Okay.
why I have joined this course.
Okay. So, are you associated with any research lab or a university?
Yeah, research lab.
Okay. 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 Thank you. So, yeah, please go ahead. Another, yeah. I think Arun Raj, he was there in the last session as well. I think he has given his introduction. He's an assistant professor at, at Vishwam Engineering College, Andhra Pradesh. Thank you, Arun. And one more person has joined, I think. Could you please unmute yourself and introduce, please? Okay, maybe the mic, there is some issue. Maybe you can introduce in the chat as well. Okay, so let's move ahead with the discussion on content of week 2. So I hope you might have gone through the video lectures of this content on rectangular and circular waveguides. As you all know, it's a rectangular or circular waveguide. Is in a way, a waveguide in general is a hollow metallic tube of either a rectangular cross section or a circular cross section. So this waveguides. So this course, this lectures in this particular week has covered how a wave propagate inside a waveguide and what are the different modes of propagation. So to just brief out and just to understand if you understood it clearly, let us have a discussion on what is basically a TE mode and TM mode and what is a TEM mode. So this is very fundamental understanding of mode propagation in the waveguide. So I suggest you please let me know what is this difference between these three different modes. TE, TM and TEM. Either you can type in the chat, or you can unmute yourself and talk. Let's be interactive so that I understand how much you could gather and how much I have to explain to you. So let's start with TE. So the expansion of TE is, yes, as you said rightly, Arun, that is a transverse electric mode of propagation. So what do you mean by a transverse electric mode of propagation? So we all know that wave propagation, there is a direction of propagation which we generally introduce with the vector k. Then there is an electric field, and then there is a magnetic field vector. So all these three are vectors. So the electric field, magnetic field and the wave propagation vector. So for with respect to the wave propagation direction, the electric field and magnetic field are perpendicular to the wave propagation, direction of wave propagation. So if I say transverse electric mode of propagation, you have to understand that, say, assuming that this is in the z direction, the wave propagates in the z direction. So in a transverse electric mode, Ez will be 0 and Hz is not equal to 0. Okay, so what does it mean? Ez is the Z component of electric field, Hz is the Z component of magnetic field. So this means that along the direction of propagation of the vector, that means the wave propagates along Z, along that direction there is no electric field, but there could be magnetic field. Okay, so the TE mode says the wave do not have any electric field component along the direction of propagation. Now, similarly, you can look at transverse magnetic wave. So, on the counterpart, I can write it as, for a transverse magnetic mode, Hz is 0 and Ez need not be 0. Okay, cannot be 0. So, in a transverse magnetic mode, the magnetic field along the direction of propagation is 0. There is no component of magnetic field along the direction of propagation. Now, how about TEM? So, in TEM, Ez and also Hz is 0. So there is no neither electric field nor magnetic field along the direction of propagation. Then we say that it is a TEM mode of propagation. So these are some of the basic understanding of TE, TM and TEM wave. Okay. So I hope this is clear from the video lectures. So let me ask you a question. I have a simple question. Please answer in the chat what do you think, yes or no. Okay. Or you can unmute yourself. Will there be a TEM wave inside the rectangular waveguide? Or I can ask this question like this: will the TEM wave exist inside a rectangular waveguide? So yes, somebody has answered no. Okay. What others think? Please let me know. TEM wave of propagation does not exist. Yes. So most of you are saying that the TEM wave does not exist inside the rectangular waveguide. That is true. So in a rectangular waveguide, only either TE mode or a TM mode, any of these would exist, either TE or TM. Now, you all know that the rectangular waveguide is a structure like this. Okay, a structure like this. And if you remember the transmission lines, you have something called as coaxial lines, wherein you had the outer conductor and an inner conductor separated by a dielectric. Okay, so here you have a tube like structure, either rectangular or circular, wherein it's like a box or circular cylindrical shape. So what is the difference here? So this coaxial conductor is a two conductor line, whereas this is not a two conductor system. So this TEM mode of propagation exists only in systems like coaxial cable, which is a two conductor system. Okay, so that is something which I wanted to understand. If you could get the concept of TE, TM and TEM modes. Okay. So I hope you have come across the solution of solving the Maxwell equations and getting the electric field and magnetic field components as a derivation in the video lectures. And also there had been discussion on attenuation in these waveguides. Okay, so let's move on to some questions so that we know how well we have understood the concept of waveguides. Okay, so coming to the first question, an air-filled rectangular waveguide has internal dimensions a into b centimeters, where a greater than b. The cutoff frequency for the TE11 mode in the waveguide is 16.62% higher than the cutoff frequency of TE01 mode. Okay, the cutoff frequency of TE10 mode is being asked. Okay, so now let's try to understand. So this rectangular waveguide is air filled. So first thing, it could be a dielectric field as well. So it indicates that the question says that it is air filled rectangular waveguide. That means it's hollow and there is no dielectric inside. So the dimensions, when we say dimensions, this is A and this is B. The longer dimension is always taken as A. And the cutoff frequency for TE11 mode. So let me ask you this: what is the cutoff frequency of cutoff frequency? What do you mean by cutoff frequency in a waveguide? Can anyone please answer this? What is cutoff frequency in a waveguide? You can even answer in the chat. What do you understand from cutoff frequency or in a waveguide?
Good evening, ma'am. Sorry
Uh,
for late joining.
yeah, no problem. So we were just having a brief of what covered in the week 2. Yes, I have an answer here. Frequency above which only propagation occurs. Okay. Frequency above which only propagation occurs. Yes, that's the right answer. So let me make it clear for others as well. So frequency above Fc will be having a propagation. Then it is very understandable that frequency below Fc will have an attenuation. Okay. So there is no propagation mode, there is an attenuation wherein the field amplitude decreases exponentially, and we call like evanescent modes. Okay, so this attenuating modes are also called as evanescent modes. Now, when we define this Fc, let me write down the equation. So we are not going into the details, but let us brief the equation. So C by 2 into square root of m by a the whole square plus n by b the whole square. So all of you know that C is the speed of light in free space. And what is m and n? What is a and b? So as I told before, a and b are the dimensions of the rectangular waveguide. M and n are the mode numbers, okay, which indicates, say, when I say TE, for example, TE11, we know that m equal to 1 and n equal to 1. So if it is TE10 mode, then we know that m equal to 1 and n equal to 0. Okay, so that is the understanding of mn. So that's the mode number. Now, coming back to the question again, cutoff frequency for the TE11 mode. Okay, so FC of TE11 is 16.62% higher than. So, if something is 16.62% above F of TE01 mode. Okay, so when something is 16.62% above, I can say, I can write it like 100 plus 16. So it comes 116.62 by 100. So it will be 1.1662. Okay, so FC of TE11 is 1.1662 of FC of TE01. Okay, I hope this is clear. So this is the statement from the question. So now we need to replace with the equation of FC. From the equation of FC, we have to write what for TE11 and what for TE01. Okay, so then we can solve this. So what for TE11? I can reduce this as c by 2 into square root of 1 by a the whole square plus 1 by b the whole square is equal to 1.1662 into second one is TE01. So when it is 01, m becomes 0 and n becomes 1. So 1 by b, so it becomes c by 2b. Okay. So c by 2 gets cancelled. Now, if you solve this, so there is one more information from the question, that is B value is given in the question as 3 centimeter. So now you have all the variables like, B is known to you. You can find what A. So I suggest all of you to please calculate and solve the numerical with me so that you will understand it better. And if you have any doubts, you can ask. Please solve for the value of A, and once you get the answer, please type in the chat. Okay, so I hope at least one of you might have got the answer. So A value is 5 centimeter. Now the question is not about finding out the A value. Question is find out the cutoff frequency of TE10 mode. Okay, when it comes to TE10 mode, m is equal to 1, okay, and n is equal to 0. So this expression FC becomes C by 2A. Okay, so now find out what is FC is equal to C by 2A. So can you now find out? This is very easy. A value is 5 centimeter. You already know the value of C. Please let me know among which of these options. Yeah, so I got an answer from, yeah, what your answer is 3 gigahertz. Yes, that is the right answer. Anub, you have something to ask?
No, ma'am, no, ma'am.
Okay. Okay, fine. So there is somebody else also answered. Yeah, B, option B, right. Arun, right answer. Okay, so it's 3 gigahertz. Okay. So I hope this question is clear. Anywhere, any doubts, please ask. If not, we will move to the next question. I hope it's clear. Okay. So let's move to the next question. Again, it's I request Anup, can you please mute yourself? Yeah, thank you. So, going to the second problem, air-filled waveguide has an internal dimension. So this is the waveguide dimensions. So this is A and B value. For this waveguide, the guide wavelength at the operating frequency is F0, which is 9 gigahertz. Okay. Okay, fine. So the question is about the guide wavelength. So you know what is a guide wavelength from the video lectures. You have come across this terminology, guide wavelength. So it's the wavelength with which the wave travels inside the waveguide. Okay. So in free space, there is an operating wavelength lambda naught, whereas inside the waveguide, the guide wave, so the wavelength changes to guide wavelength. Okay, so that is expressed in this form: lambda g is equal to lambda naught by square root of 1 minus fc by f naught the whole square. Okay, or else we can also write it as lambda naught by square root of f naught by fc the whole square. Now, based on this so you know the formula for lambda g. Now, what is given here? You are given with the operating frequency. So once if you, this is, I meant to say lambda naught by lambda c. So I meant to say that either you can express in terms of frequency or ratio, or you can express in terms of wavelength ratio. Okay. So let us first see the operating frequency is given as 9 gigahertz. Okay. So if you know the operating frequency, what is the operating wavelength? Lambda naught, which is C by F. So 3 into 10 power 10 by F is 9 gigahertz. So 9 into 10 power 9. So can I get the answer for operating wavelength lambda naught? Can anyone please let me know? Operating wavelength. Okay. So operating wavelength is 3.33 centimeter. Right. So thank you for answering. So operating wavelength, you got it. Now, the other thing is the lambda c. Okay. So what is the dominant mode in a rectangular waveguide? All of you know that it is the TE10 mode. Okay. For a TE10 mode, what is the expression for lambda c? Lambda c is equal to 2a. You all know that fc is equal to c by 2a. So lambda c is 2a. Okay. So now you know what is lambda c and what is lambda naught. Can you not substitute here to find out the lambda g? Yes. So lambda g is equal to lambda naught by square root of 1 minus lambda naught 3.33 by. So let me write. So what is lambda c? 2 into 2.286 centimeter. So you can find out this and then substitute it here and then find the final answer. So this is 4.572. So if you substitute it here, what do you get as lambda g? Yes, Arun, right? It is 4.572. So please make sure that you write the answers. I mean, when you find out some intermediate values, at least till the second decimal, you find it out so that you will match to the right option in the final answer. Okay, please take care of that because that's very important in questions like these kind of MCQs. So please take care of that. So can you please substitute and find out the guide wavelength and give me the final answer? So lambda naught is 3.33 centimeters. So I'm expecting an answer for guide wavelength. And please remember the units. Please take care of the units. See, here it is millimeters and here the answers are in centimeters. So whenever you do a calculation, make sure that you take care of the units as well. So in the interest of time, I think I would like to give the answer. So the answer is 4.87 centimeters. So it's just a matter of finding out the right answer. So you can do it. 4.87
Hello, madam.
centimeters. Huh?
Madam, without cal, see, for exam, how they will do, madam, for online exam?
You are allowed to take a calculator.
Calculator, okay, madam.
Either that or some of the online exams will have an inbuilt calculator which you can use on the exam screen.
Okay, madam. Previously, I written, madam, electromagnetic, they not allowing for calculator. That's what
So
I am
at
asking
least
you.
I hope there will be a online calculator, but I will just confirm it with the NPTEL team and get back to you.
Okay, madam.
Okay, okay.
Thank you, madam.
Thank you.
In exams, there is a virtual calculator we can use.
Yes. That is
Yes,
what I said.
because
Like there is an
yes,
online,
ma'am.
I mean, on screen. I mean, on the screen. Uh, I haven't given an NPTEL exam very recently, but as far as I remember, I had a online, I mean, on-screen calculator. So, Anup, have you attended a exam recently?
Yes, ma'am.
Okay, so what does the screen has?
Oh, sorry, ma'am.
So, is there a calculator on screen or
Yeah,
no?
yes, ma'am. Yes, ma'am.
Okay,
There
okay.
was a calculator on the screen we
So,
can use.
so you are not allowed to take a physical calculator inside the hole, right?
Yes, ma'am. Yes, ma'am.
Okay, fine. Okay. So let us move to the next question. I hope this question is clear. Then let's move to the next one. Okay. An air-filled rectangular waveguide of internal dimensions a into b centimeters with a is equal to 2b. So there is a relation between this a and b, which is given here. It's like a is equal to 2b. and this is operated at a frequency. So there is a mention of operating frequency F0. It is 30% above the cutoff frequency of the dominant mode. Okay. So FC of, so the dominant mode is always TE10. So can you tell me the relationship? How do we write this? Operating frequency is equal to how many times of FC of TE10? What should I write here?
130 into 100 upon by 100. No, sorry,
Yes.
130 upon by 100.
Yes. So that will be 1.3. I hope this is clear. So 30% above means 100 plus 30. So by 100. So it's like 1.3 times FC of TE10. Okay. So now let us write down. Okay, the question. Let us see what is the question. Question is phase velocity. So you need to find the phase velocity. So you might be remembering the expression for phase velocity from the lectures. That is, C by square root of 1 minus Fc by F the whole square. Okay. So this F is nothing but the operating frequency. Okay. Don't confuse. And Fc is the cutoff frequency of the dominant mode. Okay. So now taking the ratio here, Fc by F naught will be 1 by 1.3. Okay. So Fc by F naught can be substituted here. Okay. So Vp is equal to C is 3 into 10 power 8 divided by square root of 1 minus Fc by F naught is 1 by 1.3 the whole square. Can you not find out the phase velocity now? Isn't it easy? Can you try?
Yes.
Please try to solve it with me so that you will get a practice of how to solve the numericals. So I suggest that you have maybe you can have a calculator with you so that this session becomes fruitful and useful.
Ma'am, 4.694 into 10 to power 8.
Yes, right answer. So that is your phase velocity. Once you evaluate, you will get this answer, 4.695 into 10 power 8 meter per second. So let's move to the next question. Consider an air-filled waveguide, rectangular waveguide of dimensions a into b centimeter. If the waveguide is operated at a frequency 20% above the cutoff frequency of the dominant mode, the wave impedance. Okay, so please write it like ZTE, not like this. ZTE is being asked. Okay, so Z is the wave impedance of the TE mode. Okay, so you might be remembering the equation for ZTE, that is eta naught by square root of 1 minus Fc by F the whole square. Okay, so what is eta naught? Any idea what is eta naught?
Eta naught, I think, under root 1 minus.
Eta naught is it's a
Free
direct
space
value.
impedance.
Yes, exactly. Free space.
377.
Yes, it's free space impedance and it is 377 ohms. Okay, so you can directly substitute the value. Okay, so okay, now now let us look at the statement in the question also. The waveguide is operated at a frequency 20% above the cutoff frequency of the dominant mode. So how do we write here? F naught is equal to 20% above. So that is 1.2 FC of TE10. Okay. So now FC by F naught can be written as 1 by 1.2. So I can substitute that here. With these, you can find out what is ZTE. Can you try? Can you all try finding out the final answer? For
Yes, ma'am. 430. No, my answer is wrong.
Okay, please try again. Maybe it's just a calculation mistake.
Yeah, 453. No, it's also.
Are you taking the square of this?
Yes,
And
ma'am.
then again taking the square root of this?
Yes, ma'am.
Okay.
Six eight two.
Yes, right answer. 682 ohms. So that's the right answer. So let's move to the next question. Okay, so far we had a few questions on rectangular waveguide. So now let us talk about circular waveguides and solve some questions on circular waveguide also. So in case of circular waveguide, as you all know, so basically it's the cross section. So it's like a cylindrical kind of structure. So okay, so a circular waveguide, generally we say we denote it with the radius of the circular cross section, and we express so sometimes this R is also represented with the letter A. So the cutoff frequency in a circular waveguide is given by rho nm divided by 2 pi a root of mu epsilon. Okay, so let me just try to make you understand what is this expression. So rho nm is a value based on whether it is a TE mode or a TM mode. So this has to be taken from this particular table, which I am just showing in the slide right now. So this kind of information or the table will be given to you to find out the value. You cannot memorize these numbers. So these will be given. Okay. So one thing to notice here is this is for TE and this is for TM. Okay, and the numbers here. So if you look at this, say for example, you have a TE10 mode. You know that it is m is equal to 1 and n is equal to 0. Okay, so you have to select the TE mode table and m equal to 1 and n equal to 0. Okay, so this will be the row 01 is equal to 3.832. Okay, so in case of a TE10 mode, the row nm, the corresponding row nm will be 3.832. Okay, and A is nothing but the radius of the circular cross section. And what is mu and epsilon? Say, for example, if this is air-filled waveguide, this mu and epsilon reduces to mu naught and epsilon naught. Okay. If it is not an air but a dielectric, then it has to be replaced by mu epsilon, which is nothing but mu naught into mu r, epsilon naught into epsilon r. Okay. So mu epsilon will reduce to mu naught epsilon naught if it is air filled. If it's dielectric filled, we have to simplify it like this. Okay. So this is some basic idea of how to use this equation. So let us look at one question. A dielectric filled circular waveguide. So you notice there is a dielectric and it's a circular waveguide. It has a cutoff frequency 5 gigahertz for the dominant TE11 mode. Okay. Now there are many things here. Have you noticed the dominant mode for rectangular waveguide? We used to say TE10 mode, but here it is TE11 mode. In case of a circular waveguide, dominant mode is TE11. Now, what is given here is the dielectric constant value is given 1.69 and also the cutoff frequency is given as 5 gigahertz. The question is the radius of the waveguide or R or A, what it is. So let us first write the expression rho n nm divided by 2 pi a into root of mu epsilon. Okay. Now let us see the mode TE11. So m equal to 1, n equal to 1. Okay, m equal to 1, n equal to 1. Can you tell me the value from the table? What is the row nm? Can anyone please type in the chat? For TE11 mode, what will be row nm? Look at the table for TE mode. Yes, right. It is 1.841. Okay. So 1.841 divided by 2 pi a. Now FC is given, you know FC 5 gigahertz and square root of mu naught epsilon naught mu r epsilon r. Mu r is 1 and epsilon r is 1.69. Now, do you know what is 1 by root of mu naught epsilon naught?
C.
C. So you can replace this like C. Okay. So 1.841 into C divided by 2 pi A into square root of 1.69 is equal to 5 into 10 power 9. Now, can you find A? So A is nothing but the radius of the waveguide, which you are trying to find out. See that it should be in centimeters. I hope somebody might have got the answer. Can you please let me know if you get some answers for the value of A?
Yes, ma'am, 0.0135.
Okay. Yes. So let me know the answer in centimeters.
35.
Yes. So as you see, it is 1.35 centimeters. So make sure that you do such conversions appropriately based on the question. So I would like to ask if you have any particular doubts in the particular, I mean in the last week. So because I think the assignment submission for week 1 and week 2, the deadline is I think August 9th. So maybe we will not have a session before that. So if you have any particular doubts in the week 1 or week 2 content, let me know. If possible, I can try to answer those.
Okay, ma'am.
Okay, so you can even email or you use the discussion forum. So I think I haven't looked at the discussion forum last week. So probably if you have any questions, you can ask me. Okay, so we'll move on to the next question then. So in a circular waveguide, cutoff frequency for TM01 mode is 6 gigahertz. Cutoff frequency of TE11 mode is. So you are given with the cutoff frequency of a particular mode, you are asked to find the cutoff frequency of another mode. So remember that it is for a circular waveguide. Okay. So how do we solve it? Again, use the expression of Fc rho Nm divided by 2 pi a square root of mu epsilon. Because there is no information of dielectric field, we take it as air field. So we can write it like mu naught epsilon naught. So I can even write it like this, rho Nm into C by 2 pi a, which is the FC equation. Okay. Now use that here for TM01 mode. Okay. So what do we do? M value is 0, N value is 1, and it is a TM mode. Get me the value of rho NM. So tell me what is the value of, so the mode is TM01. So you must know what is rho NM. Rho, so this is like MN, so 1, 0, rho 1, 0. Can you please get the value of rho 1, 0 from the table for a TM mode? Yes, Arun.
Yeah, there is a problem here.
Yeah, just a minute.
And
Mhm. Okay, I think we can solve this question in a different way also. Just a moment. We need not have the table values here. Okay, so let me just write it down. The expression for FC TM01 is rho NM divided by 2 pi A into root of mu epsilon. FC of TE11 is rho NM divided by 2 pi A into root of mu epsilon. See, this is written as 6 gigahertz. So 6 into 10 power 9. Okay, sorry, there is a error in the question. Let me just correct it. So this is TM10. So TM10, okay, TM10 mode. So M value 1 and N value 0. N value 1 and N value 0, it is 2.405. Okay. So please let me correct the question here. TM10 mode. Okay. Okay, thank you. So this FC is rho NM by 2 pi A into root of mu epsilon, mu naught epsilon. No? So this becomes 2.405 divided by 2 pi A root of mu naught epsilon naught. Maybe I can just write it like C. is equal to 6 into 10 power 9. Now the second is FC of TE11. So from the TE table, TE11, it is 1.841. So 1.841 divided by 2 pi A root of mu naught epsilon naught, which is 1.841 C by 2 pi A. Okay. So now from here you can find the value of A and substitute back here and find out FC of TE11.
Then 4.607.
Just a moment. Yeah, the answer must be 4.59. Are you getting that? Yeah, 4.59 gigahertz. Okay, so approximately it is like 4.58. We are close to 4.58 gigahertz.
Okay.
Okay. So you can always take the closest number among the options. Yeah. Okay. Now coming to question number 7. An air-filled rectangular waveguide has A is equal to 2B and A is 3 centimeter. So this is about rectangular waveguide which is air-filled. Now there is another circular waveguide, okay, of radius R which has the same cutoff frequency. So FC, the cutoff frequency of rectangular waveguide, they are saying that it is equal to circular waveguide. Okay, so this circular waveguide has a radius R and this rectangular waveguide has a dimension like A cross B where A is equal to 2B. Okay. And it is also given that A value is 3 centimeter. So, the one thing to note here is it has the same cutoff frequency for the dominant mode as that of the rectangular waveguide. So, we need to also remember that this is with respect to the dominant mode cutoff frequency. So what is the dominant mode cutoff frequency in a rectangular waveguide? In a rectangular waveguide, the dominant mode is T10. And how about the circular waveguide? T1. Okay. So now let us write the expression and try to equate. So how about FC of rectangular waveguide for TE10? So I can write it as, you know, the
0.28 C by 2
into root of square root of m by a the whole square plus n by b the whole square. I think no need of explaining this. This goes to 0 and I can write this as C by 2a. Okay. So this is the cutoff frequency of the dominant mode of the rectangular waveguide, which can be equated to the dominant mode of the cutoff frequency of the circular waveguide. So circular waveguide case, it is rho mn by 2 pi a square root of mu not epsilon naught because it's air filled. So this rho mn will be rho 11. Okay. So what is rho 1? So this has to be equated to rho 11 by 2 pi a. Instead of a, I will write it as r because a is confusing here. Basically, a is the longer dimension of the rectangular waveguide and r is the radius of the circular waveguide. Okay. So 2 pi r root of mu naught epsilon naught. So this can be written as c. So here c and c gets cancelled. 1 by 2a is equal to rho 11 by 2 pi r. Even 2 gets cancelled. So Can you tell the final answer for the value of A? You must know row 1, 1. Row 1, 1 for T.
1.758. 1.758.
Okay, let me check. So, row 1, 1 is 1.841. So, A value will be pi R by row 1, 1. Okay, fine.
1.758.
Oh, sorry.
1.76.
I made a mistake here. R is row 1, 1 by A into row 1, 1 by pi. So, what is the final answer you're getting?
1.758.
Okay. Yes, right. That is true. 1.76 centimeters. Okay. So if you have any doubts in the, whatever problems we have solved so far, please do ask. So I have a suggestion. I have a question right now on the screen. I suggest you please go through the question and try to understand. So this is a question from rectangular waveguide. You are given with the value of A and B. Okay. In sigma mu equal to mu naught. So this means that this is about the medium inside. Okay. So A and B, as you know, it's the dimension. Sigma is basically the conductivity. It's saying that 0. Mu is equal to mu naught and epsilon naught is equal to 4 epsilon naught. So that means there is a medium which is having permittivity as 4. Okay. So the expression what is given here is Hx. Okay. What do you mean by Hx? It is the x component of the magnetic field. Okay. And it is given as an expression. Okay, you know that how the usual expressions look like. So it's of the form of h naught into sine pi x m pi x by a multiplied by cos of n pi y by b, and then sine of or something like omega t minus beta z, that kind of form. So the first question here is, what is the mode number of operation? So if you are given with the expression for a magnetic field component, can you not find out the m and n here? Can you try looking at the expression of the magnetic field x component? Okay, so I got an answer here. It is m equal to 1. Sorry, m equal to 1, n equal to 3. Okay. So, how did you arrive at this? Can you please explain how did you get this?
Ma'am, the standard equation for Hx is h naught sine n pi x by a into cos m pi by b
Yes,
into
right.
sine omega t minus
So,
beta.
this is of the form sine m pi x by a cos n pi y by b sine of omega t minus beta z. So you know this. Now, what is the mode? So now this is just a mode number. Can you tell what is the mode, whether it is TE or TM? So I have both answers. So Arun, can you tell why you say that it is TM?
But HX is not equal to 0 now. But TM mod is.
HX is not equal to 0. Okay. So what is the propagation direction here? What do you think is the propagation direction?
Z
Yes,
direction, madam.
Z
Beta
is
Z
the
is Z.
propagation direction. Yes. So you are saying that, so it is a TM mode. Okay. Anu, do you have something to say?
Hello.
Hello. Please go ahead.
Ma'am, we can define T or TM modes for HZ and EZ.
Mm.
According to HZ and EZ, we can define now.
Yes.
This is T
Yes.
or TM mode. So,
Mm.
so
So,
why we consider
what is
HX
your
here?
understanding from here? So, here it is HX.
Yes, ma'am.
So, what is that you are understand from here? You can understand that HZ is 0.
Then we can say that this is TM mode.
Yes. So, HZ is
And
0. So, we say that it is a TM mode. So, to make
hmm,
it clear, it is TM13. Okay.
just that.
Okay, fine. So now next question is determine the cutoff frequency of the mode. Can you please find out the cutoff frequency of this mode? Use the expression FC. Expression for FC. I request all of you please do try C by 2 into square root of m by a the whole square plus n by b the whole square. I will give you time to calculate. Please do try. You have the value of mn, you have the value of a and b, and you also know the value of c.
Here C upon 2 and under root 4 because there is a relative permittivity.
Yeah. Please. Oh, yeah. Please. I just missed it by root epsilon r.
Hello, ma'am.
Hello.
Uh, I think this answer is 0.28 gigahertz.
0.28.
Yes, ma'am.
Okay. Anybody else with the answers? Please type in if you cannot use your mic. Please type in your answers. We'll wait for a couple of minutes. Meanwhile, Anup, you can check your calculation for
Mhm.
just for
Yes, ma'am.
units.
Okay, ma'am.
Okay, so I think in the interest of time, I'll just write down the final answer. It should be 28.5 gigahertz. Please see the units. So whenever you say C is 3 into 10 power 8 meter per second, make sure that you substitute the value of A and B in meters, or else you can put it as 3 into 10 power 10 and then directly substitute the value of A and B. So you must be getting the answer 28.5 gigahertz. Any doubts? Okay, right now I have a question on screen. Please do, this is a slightly different question. Please do try this. So you are given with a section of rectangular waveguide of cross section 2 centimeter into 1.5 centimeter. So this is A value and this is B value. And this has to be used as a delay line in a radar at 10 gigahertz. So it would be the operating frequency of the radar. So it is used as a delay line. And what should be the length of the section to realize a delay of 10 nanoseconds? So you have basically a rectangular waveguide, a section of rectangular waveguide, which will be used as a delay line. That means it is introducing a delay. Okay, so the wave is propagating, it is introducing some delay for that wave propagation. So the question is to get a delay of 10 nanoseconds. Okay, I am saying that I need a delay of 10 nanoseconds. What should be the length of this particular section? Okay, so to get this clear, so I hope you remember the concept of phase velocity and group velocity. So the phase velocity is the velocity with which the phase moves, whereas the group velocity is basically the wave propagation velocity inside the waveguide. Okay, so we say the energy flows or the energy packet flow is at a rate of Vg, that is the group velocity. So this Vg is the velocity, time delay is 10 nanosecond. Can you find the length? Okay, so the simple relationship between velocity, length and time delay, you know that Vg can be written as L by TD. Okay, so what is L? It will be Vg into TD. So can you find the group velocity? If you can find the group velocity multiplied by time delay, you can find the length of the section, which will give you a time delay of 10 nanosecond. Okay, so now how do we find group velocity? So what is the expression for group velocity? Can someone please tell me what is the expression for group velocity? Group velocity Vg. So let me write it down for you. C into square root of 1 minus Fc by F the whole square. Okay. So here, you know the operating frequency F naught. You have to substitute something called as Fc. So what is Fc? That is the, you need to see the dominant mode and the cutoff frequency and substitute the value of Fc there. So, let us first find out the Fc value. In case of dominant mode in a rectangular waveguide TE10, so C is C by 2a. So C 3 into 10 power 10 by 2 into a value is 2 centimeters. So 3 by 4, 0.75 into 10 power 10, or I can say 7.5 gigahertz. So that is going to be the FC, and F naught is 10 gigahertz. Okay. So now can you find VG? Can you all please try VG
Yeah, yes,
value?
ma'am.
Please type in the answers for VG, the group velocity, if you could find. So the ratio FC by F0 will be 7.5 by 10. So 0.75 basically. So 3 into 10 power 8 square root of 1 minus.
And my hello.
Yeah. Please go ahead.
Well, the value of this is 0.999.
Did you take any approximations? I think you must be getting 1.98 into 10 power 8 meter per second. Please do recalculate once again. Okay. So once if you know this, just multiply 1.98 into 10 power 8 with the time delay is 10 nanoseconds. 10 into 10 power minus 9. So what will be the length here? Answers please. It will be 1.98 meters. Okay. So the length of the section of this waveguide should be 1.98 meters so as to get a time delay of 10 nanoseconds. Is it clear? Any doubts?
No, man.
Okay. So are there any doubts with respect to the content of week 2 or week 1? I request if are there any questions which you would like to revisit, which I have solved today? Are there any questions? If not, we will wind up today's session. Thank you all for joining. Thank you for your attention. And I request you guys, please have a calculator. Please try to calculate, solve the questions with me so that this gets better. The assignment solving also, it helps in assignment solving also. And we are not actually discussing any of the theoretical part mostly because the session itself is named as a problem solving session. So I would suggest please have a calculator and try to solve it, and let us be interactive in that case so that we will know where is our strength and where is our weaknesses. So thank you all for joining today. And
Madam?
Yeah, please.
Madam, Sunday class last week not connected, madam. 5 to 7.
Okay.
Yes, ma'am. Yes, you.
Okay. I'm not sure of what has happened. Probably I'll find out